Welcome back to Odds Learning. In this video, we'll be going over the master equation, the equation behind all types of conservation of energy. Okay? Maybe not all of them, but the most general equation you can have at the stage you're in. You can add to it later, but for right now, this is the most comprehensive it can get. This is your equation. Work non-conservative plus kinetic energy initial plus potential energy initial plus energy spring initial is equal to kinetic energy final plus potential energy final plus energy spring final. Okay? So what does this mean? This all follows one basic principle. The principle of conservation of energy, which I explained in my previous videos, right? Energy cannot be created or destroyed. It can only be conserved through transformation. Whatever total energy you start with, it's going to be the total energy you end with. This is what the conservation of energy principle says. So what does each one of these terms mean? Work non-conservative is work done by non-conservative forces, okay? You remember when I explained non-conservative forces, I said those were applied forces, right? Where you could push or you could pull. Or there could be friction or sound, right? Or heat. Lot of scenarios here. But these are your non-conservative forces, okay? Plus the kinetic energy initial, I stands for initial, plus potential energy initial, plus energy due to spring initial is equal to kinetic energy final, plus potential energy final, plus energy spring final. At any given time in this course, the hardest question you're going to be given uses every single one of these terms. But it can't get harder than that. So that's the good part. So it makes sense, right? All the initial energies have to make up to the final energies, because that's what conservation of energy is. You start with something, and you're going to end with that same thing, right? Same amount of energy. So you can obviously substitute in kinetic energy for 1/2 mv squared, potential for mgh, 1/2 kh squared, okay, for spring. And if you start with a certain amount of energy, you're going to end with it. So suppose you started with full potential energy and none of these, right? Then you're going to end with probably full kinetic energy or no potential energy and no energy spring, right? It could happen. There's multiple scenarios. And work non-conservative is just the force, right, times the distance. So the reason we put that over here is because you start with that work, right? Or imagine if this was force of friction times d, right? Then what can we say? We know that if you subtract this from both sides, this is going to be minus force of friction times d, which is right? Because force of friction times d is a negative value here, because that's pushing against your other energies, right? That's subtracting from your total energy. It's dissipating it. But here, guess what it would be? It would actually be plus. The negative is just a common misconception, okay? That's why I was walking you through it to try and see whether you catch it. It's not true, because the total energy here, no matter how it's dissipated, must make up to the initial energy, okay? So here it'd be positive, and then if you subtract it, this would just be negative here. So you'll understand what I mean when I go over it more to the problems, right? Because that's how you learn at OTS. You're going to go through the problems and you learn from harder depth, not harder lectures. But we'll go over it, okay? So don't worry about it if it's not too much sense making right now. But let's start with the 4 steps that you need for any kind of problems involving that equation. You have to pick your start point and your end point, okay? Then you can measure your energies at those points. And then you list the energies at each point. because you have multiple energies, right? You want to look at every single one of them, and you want to see which ones do you have. And you cross out the zeros, because there could be some that don't exist, right? You identify work non-conservative. Applied friction is negative. Applied is positive. And neither is zero. Because applied is like, you start with an initial force, right? So plus kinetic energy initial, blah, 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 is equal to kinetic energy final plus blah, blah, blah. But if you start with an additional force, right? So force applied, let's just say, times distance, which you could push the block, then you're going to start with that energy as well, right? So that energy must also be made up by, because if you push the block harder, then you're going to have more kinetic energy here, right? So this energy increase would make an energy increase here. But friction would be negative, which I explained before, right? Over here it would be positive because it has to account for the missing force. And then you subtract from both sides, it's negative. Okay? And then you substitute and solve for the one unknown. You usually don't get multiple unknowns here, but there are a few cases where that happens, but the main scenarios are you have to solve for one type of energy or one mass or velocity or spring constant, right? And you can just plug those in to find that. And then you could solve for like K or M or V. So now let's try a problem before we jump into the other problems. A 2 kg apple, okay, from rest drops height is equal to 3 meters, okay? So it drops this much height. No friction. I mean, pretty obvious, right? Because the ball can't have friction in air. But if you do fall down, guess what it's trying to say is, if you bounce up, that's friction, right? Because it takes over here the sound and the heat. But you don't need to worry about that, okay? Because we'll consider this as our ending point. If you do, then we don't need to worry about the bouncing off. Okay, so let's start with our master equation. Work non-conservative, do we have that? No, right? There's no applied force or friction force. Plus kinetic energy initial. We start from rest, so we don't have kinetic energy. Plus potential energy initial. We do have potential energy, so I'm going to keep that. Plus energy spring initial. We don't have that either, so it's just potential energy initial. Is equal to what? At the ground, potential energy is 0, right? So that means this at the ground has to be kinetic energy final. Plus, that's it, right? Energy spring, we don't have that. Potential energy, we don't have that. So it's just this. So mgh initial is equal to kinetic energy final, which is 1/2 mv squared. So we can use our 2 kg as our mass, 2 kgs. This is 9.81 meter per second squared, gravity, right? Times height initial, which is 3 meters, is equal to 1/2 times 2 kgs times v squared is what we're trying to solve for. Okay? So if you have your calculator out, which you should, right? These problems get very messy very quick. So the left side is just going to simplify to 58.8 joules, okay, is equal to v squared. So the square root of that is just 7.66, or approximately 7.67 if you round up, meters per second. And that's your answer, okay? That's how you find quantities using the equation of conservation of energy. So let's try some more problems. As always, make sure to pause the video and try yourself. And then I'll walk through with it with you. Okay, I'm assuming you gave it a try. Let's get at it. A 3 kg block, so 3 kg here, is released from rest and drop's height is equal to 2.5 meters with no friction. Write the master equation and solve for the speed of the block just before it lands. Okay. So let's do that then, right? Do we have kinetic energy initial? No. Do we have spring energy initial? I don't see any springs here. Do you have work non-conservative? No applied force or friction either. But we have potential energy initial. And at the end here, gravity is going to be 0, right? I mean, not gravity, height is going to be 0. So potential energy final is 0. Energy spring final is also 0. There's no springs. And kinetic energy final is not 0, right? Because it has a speed when it lands right before. Potential energy initial is mgh is equal to 1/2 mv squared. So there's two approaches to this. You can just solve the problem by plugging in the numbers now. But if you wanted to make it a tad bit easier, we could just divide by m on both sides, right? Before we even substitute anything in. So then we could do 2gh is equal to v squared, and v is equal to square root 2 times 9.81, or just 9.8 times 2.5 meters. Okay? Or in other words, square root of 2 times 9.8 times 2.5, or 7 meters per second. Always remember your units. Okay. So we need to look back at the drop in question 1 and write out every term of the master equation. Mark which ones equal 0 and give a one-line reason for each 0. Okay, so kinetic energy initial, but we started at rest, right? Since we started at rest, no movement, no velocity, which means 0 kinetic energy. Because 1/2 mv squared, if v is 0, the entire thing becomes 0. Potential energy initial, so that we don't need to mark out, right? Because it's not equal to 0. It does have a value. Work non-conservative, no applied force or friction. So there's no work non-conservative. And spring energy initial, there's no energy spring because there's no spring, right? We're not hanging off a spring or anything here. So no spring in sight. And same reason for energy spring final. We don't have a spring. Potential energy final is 0, right? Because when it hits the ground, it has a height of 0, which makes it just cancel out to 0. Because all the potential energy has to go to all the kinetic energy. Energy needs to be conserved, right? So let me include that as well. And last term, which was, I believe, kinetic energy final, we do have. So we can leave that. Okay? Everything else looks good. Right? Yeah. So now let's move on to the next slide. Okay. So we have a 2 kg block that slides 4 meters. Okay, 4 meters across a rough, flat floor with mu k is 0.2 and comes to a stop. Here, the non-conservative work term is not 0 because we have what? not applied force, but we have the force of friction. So we need to set up the master equation with friction in our mind, okay? We can't forget about it this time. And we need to solve for how fast the block was moving when it started. So this when it started tells us what? It was the initial position. Initial what? Velocity, right? So we need velocity initial. So probably kinetic energy initial. So if I write on my equation, work non-conservative plus kinetic energy initial plus potential energy initial plus energy spring initial, energy spring final plus kinetic energy final plus potential energy final. Which of these terms can cancel out to make 0? We do have an initial kinetic energy, right? Because we're sliding across. We can't do that without a velocity. Work non-conservative, we have that as well. Potential energy initial. Do we have any height here? No, right? So we don't have that. Energy spring initial, we don't have that either. Energy spring final, no springs. Kinetic energy final, it comes to a stop, right? So velocity final is 0. So kinetic energy final is also something we don't have. And potential energy final we also don't have, because that's, we don't have a height, right? So the entire thing is basically just kinetic energy initial minus force of friction times d, which makes sense, right? This has to match up to this to make it 0. That's why the block can come to a stop. That's why anything you roll on the earth comes to a stop, because of the force of friction. So I could probably simplify it to just make it look a bit cleaner. I could write this as force of friction times distance here. So I can add on both sides to give it a positive value. Okay, so this is 1/2 mv initial squared is equal to mu times, there's going to be a lot of letters here, but luckily we don't have mg cosine there, right? Because this is just gravity. It's just mg pulling us down here, so we're just going to match that up with it. A normal force equal to mg, because that's our normal force, right? Then times d. So we can divide by m on both sides. And we get, let me actually clean up some space here. We get v initial squared is equal to mu times 9.8 times distance, which is 4 meters, times 2, right? Because of this 2 here. And then we can just square root that. So v initial is equal to square root mu 0.2 times 2 times 4 times 9.8. This should just give me, so let me try and compute that. About 3.96 meter per second. There you have it. That's your answer. Your velocity initial. A cart starts with 40 joules of kinetic energy and 60 joules of potential energy. And friction does negative 25 joules of non-conservative work. Find the total mechanical energy. So mechanical energy is another phrase you need to know. Okay? I think we went over it before, but if you don't remember, a quick recap. Mechanical energy is just kinetic energy plus potential energy. Okay? It's none of the other energies. So it counts as energy spring, but it's mostly just used for objects that are falling. Okay? Because if a ball was falling, then potential energy and kinetic energy would both be there, right? Except at the extremes. The extremes when it's dropped, which is only potential energy and no kinetic, and the extreme when it hits the floor, which is only kinetic and no potential. Okay, so we need to find the total mechanical energy and say which term of the master equation the negative 25 joules belongs to. Okay. And we need this mechanical energy. We need this mechanical energy at the end, right? So this should be kinetic energy final plus potential energy final. So let me write out my equation. Work non-conservative plus energy kinetic initial, or kinetic energy initial, plus potential energy initial, plus energy spring initial is equal to energy spring final plus, let me get this little ball out of the way, potential energy final plus kinetic energy final. So you can work non-conservative will become negative 25 joules, right? So we can also just get that out here. Negative 25 joules belongs to which term of the master equation? Work non-conservative. Plus kinetic energy initial is 40 joules because it starts with, right? So these are both initial values. Initial. Plus 60 joules is equal to kinetic energy final plus potential energy final, which I can just write as mechanical energy, right? Because the reason for that is it's not asking us for any specific value, right? It's just asking us what's kinetic energy plus the potential energy. So I can just represent that as mechanical energy, right? Then energy spring final is just 0. Then energy spring initial was also just 0. So this is going to be 100 joules minus 25 joules, or in other words, 75 joules is mechanical energy. Final, mechanical energy final. Yeah, you want to remember that, right? And that's it. There you have it. Next time, we'll be ramping up these questions, okay? Because these questions in tests, they're going to appear almost impossible to decipher. They're going to look like hieroglyphs because there's a lot more versions of these and ramps as well. So that's what we're going to be looking at in next video. So feel free to stay tuned and give me a like and subscribe so I can keep pushing out content like this and helping you as well as others.